So today again in this video we'll continue the solution of the state equation. Now what we had studied in the last video, that instead of taking a direct approach, we took a system described by this. Yes, where is that equation? Yeah, sorry. We started with that, with assumption that all the entries of this AT is continuous and well defined. Well defined means finite and continuous over for all value of time in the interval, and then instead of we were investigating for to establish the fact that a definite solution exists for this system. Now for that one, instead of taking a means rigorous mathematical approach, we did something that is slightly unscientific but still holds means good for engineer. That is, we took uh, means a sequence that with an assumption that if we go on increasing the value of k, it will somehow like it will be a sequence vector that is going to approximate solution for this equation. I may make some mistake in that spelling of approximate, because quite often I get confused in the spelling of approximate, apology, all this, where it is double P and where it is single P. So anyway, this is the solution also defined for this closed interval. It was our, we start with that. Eventually, where we ended up, we then define two constant. One is alpha, that is max of and another one is beta. Both are time invariant clearly. It was our beta. Then what we did, finally we approached to a condition where we got this is the end result. Let me write it in different color, and the bound of right for j is equal to 0, 1, 2, like this. So then what we claim, that it is basically the solution is a series whose bound is given by and this is going to converge at this upper bound can be expressed in this way, like obviously this one is directly you can write in this way, and for any finite t you are having finite means a solution that converges. So it is basically we have the proof that for a definite value of t, our solution does exist, and then also we figure out something that is our, we call it like a state transition matrix. Let me write it once again. Into x naught t naught, or you can write it like x naught x, oh god, x naught. So this one we then consider this like xt is equal to this whole bracketed term. We write it by phi t comma t naught x naught and term this as state transition matrix that we have discussed in our last video. Also we claim that this will exist for now. Here this t is belongs to that interval t naught plus t. What we need to show that this whole means it's true for any arbitrary value of t, like what we can means in a more generalized way we can prove this for any finite t greater than 0 this solution exists. So if this solution exists for any arbitrary t, then obviously it makes sense that like this whole thing we can use, let me write it once again in the form like I am writing it in some other form. Don't get confused, just open your eyes and you will figure out that exactly the same thing. I am just changing the variable to make sure you do not get means you do not develop any prejudice with any variable. Rather, you should be very means comfortable with switching of variable. What was T naught, now it has become tau. There are many intelligent, means over smart student I know exist in this batch who always suggest me what to do, what is good, what is bad. Like I always welcome suggestions, but problem is that if your suggestions reference or means is based on something that is impossible to achieve or means totally irrelevant, then it becomes a bit more troubling. Anyway, they will do what they want to do. I don't want to restrict anyone. It's like that. So let this be an equation, say equation 1. Let us number, otherwise we cannot. So this holds good for any tau that belongs to this range for any arbitrary value. You can have this convergence of this series is its series is absolutely and uniformly convergent. That can be proved using a theorem that I am not going to discuss, but this form of definition in this state transition matrix, like you are having integration, it is defined as Piano-Baker series. No need to means just get means no need to lose your calm and get means totally obsessed with this piano Vika series, hit Google and this that. Just what this piano Vika series ensure us that we can prove that this series is uniformly and absolutely convergent for any arbitrary t in this region. Well, so now we'll prove that this is the only one solution that exists for our case. So in order to prove that uniqueness, here we will utilize our means once again we will take help of one theorem that is known as Grunwald Bellman inequality. So here what we will do that, suppose that we have a function phi t and our vt are two continuous function defined for and suppose let us have psi a constant, like psi is a constant, right? Then the implicit inequality then the implicit inequality, this inequality implies the explicit inequality so let it be equation 2 and it be equation 3, otherwise I cannot take track of this. So what we are claiming, that is very simple thing, and means just by means common intuition, or means if you are having slightly imagination ability, you can figure out that obviously if he is in such way defined, then this phi t is going to be means upper bounded by this, right? Anyway, let us prove that perhaps we have reached the end of the page, so we need to go in the next page. Let us write now, like sometimes I may write here tau, sigma, gamma, lambda, whatever I want. Don't develop any prejudice with any dummy variable. All these are dummy variable. So be very free with the use of variable, right? So don't always need to be like a first year student that said why you are writing this, that. Apply your common sense to understand that as long as it is dummy variable, we are means free to do that. Why we have written this like RT? Just because it is something like the same thing that was there, but we start with the equal case. like phi t was less than is equal to, and here RT is equal to. So then we can write R dot T, as we have already mentioned, psi is constant. It is equal to what? It is equal to Vt into phi t, right? Now here one thing that is that we should not forget, that Vt, I have mentioned in the last page that Vt by definition, Vt is where it goes. Yeah, Vt is always non-negative, right? So if Vt is non-negative, that is very means important property here. What you can say that R dot T is equal to Vt right, and let it be equation number 4. Now let us multiply both sides with your let us multiply both sides with so what you will get here, you will get this one, like if you multiply, then you will get okay. Now tell me whether this function, this one, is a positive function or negative function. Think about it. Whether what is the sign of this? If you evaluate this integral, for obviously I will give you t naught and t. So what you will get? So now what you will get here? It's very clear that once you multiply this, you will have like we are multiplying this one with both side, and you will see that when you multiply this with this side, then it will give you something that is less than means you are getting this form. And if you still have doubt, let me show you how you are getting this. Okay, do not let us not waste our time. Just it's a side transposition. If you just multiply it and then you take it here, you will get this, right? Only thing is that here the sign of this will matter. That is why I asked that what is the sign of this one. So if you are interested, just let me know what will be the sign of this one. Sign of this gentleman. Right. So now let us integrate both sides of this one. Obviously one side is 0. So if you integrate both sides, then what you will get, that is very interesting. You will get RT So basically, when you do this, what it actually yields? It yields that you are getting the point from where you started. This gives us you the equation number 3. What was there in equation 3? We were trying to prove this one, and see, we got this one. So now this is kind of that we are interested to show the uniqueness of the solution. Like this can be proved by negation, or what is that like, or what we can do, not negation, like we can start with two different seemingly different solution, and then eventually we reach to a point where we will see that the two solutions are actually the same solution. So let us consider that we are having two solutions like XA and XB. So given T naught and X naught, we are considering XA and XB, both are your solution, and both of them satisfy this equation with XA and XB, both of them satisfy this equation. So what you will expect? Let us define, as XA and XB are as per our claim they are different. We can define another their difference like ZT is equal to this. Now obviously therefore Z dot T will satisfy what? It has to be 0 because your so this implies this has to be 0. Now see, what is our objective of having this equation? That this implies like how we can prove that the two solution XAT, this sign is known as identically. Again, I am a bit confused with number of L here, so please check it. So here, how we can ensure it? Only when we will be able to prove that ZT identically equal to 0, and that can be means we can prove only when we can prove that Z dot T is equal to 0. That is what happened in your equilibrium point, although we are not here talking about not equilibrium point, but in equilibrium point the means rate of change of state variables becomes identically equal to 0. So our objective is to prove that ZT is identically equal to 0. Now this one, this zt is clearly a solution of this equation, right? It's a trivial solution. Trivial solution, it is a linear homogeneous equation. So that is why a trivial solution you can always get. Now, let us take that kind of means, let us do integration of this whole thing and let us see what happens. So if you integrate, what you will get? You will get that just a minute, someone is calling me. So this is less than this one, fine. So now clearly, if you apply the previous discussion with where it goes, now here, if you consider that this person is equal to 0, then here it becomes clearly that now this one is almost equivalent to what we got, because V is positive and like the other party will be must be present in the both side. So it gives us that phi t should be less than is equal to 0. Now see here, there is a possibility, this leaves us with a possibility that, where it goes, this leaves us with a possibility that mod zt, this one, this norm can be less than is equal to 0, but as this is norm, so it cannot be less than is equal to 0, it has to be is equal to 0. It implies z2 t identically is equal to 0 for all t belongs to this set. So x-ray t is identically equal to xbt. So we have proved the means uniqueness of our solution. Now we will see that again. Let us write a theorem that is based on Piano-Becker theorem, that for any t naught and x naught, the linear state equation x dot t is equal to at xt, where entries of at are continuous and well defined, and then we will have a continuously differentiable solution in the form of and the state transition matrix is that one which we given by the piano maker series is like this series is absolutely and uniformly convergent for arbitrary value of t and tau belongs to this minus t comma t, where this t are t greater than 0, they are arbitrary. Now this is all about linear state. Obviously when we will go to non-linear case, things will become pretty different than what we are having here. In case of non-linear system, what we are having, say, let us take one simple case that is given by x dot t is equal to say so here you can see that this has you can prove also this has two distinct solutions. One is so clearly the solution is, rather the solutions are non-unique. Now if you take another example like then you will get but at the time interval this is solution is defined or means exist only in this time interval, but at t is equal to plus minus pi by 2 this solution doesn't exist, right? But it's no longer continuously differentiable, and like it is difficult to means claim that this solution exists. Now in our next video we'll discuss complete solution. As we are having a few minutes in our hand, I would take the I would like to utilize this time just to discuss in a very concise manner that how you can understand that for non-linear system, or means for any system, any dynamic system, whether your system will have so what we should do if we have a system in this form. Then we must check whether this one is Lipschitz continuous with respect to x. Like what is Lipschitz continuity? Lipschitz continuity says that if you take two values, like let me give you one example. Say, just a minute. Lipschitz function. What is Lipschitz function? Say a function is Lipschitz So, if a function f is Lipschitz, then it will satisfy this condition. Then we can say this is a Lipschitz function. So, I can give you one example of such, like if we take x comma y is equal to, let us take f t comma x is equal to 3x plus 2, then we can have f of t comma x1 minus f of t comma x2. So that will result in 3 of x1 minus x2. So here the Lipschitz constant is what? Lipschitz constant is L is equal to 3. Like here what we are claiming, that is very simple thing. The rate of change of your function is here our L is 3. Now another example, we can see that a function which is not Lipschitz. Let us take one example, f of t comma x square. So what we will get? It is t comma x, that is t x square. So what you will have here, f of t comma x1 minus f of t comma x2 will be how much? T of x1 square minus t of x2 square, that will be t of x1 minus x2 into x1 plus x2. So here you can see that it is not bounded, because if we try to compare it with the standard form of Lipschitz equation, that should be f of x1 minus f of x2 less than is equal to L x1 minus x2, and L should be finite. However, this t x1 plus x2, if you compare, then this need to be L, but for that L is no way a finite number, because if you go on increasing the value of time, then obviously your L will be very high. So what we can say, that this f is not Lipschitz with respect to x, right? But in some other cases it can be Lipschitz, like if you take it, means try to check its whether it is Lipschitz with respect to t or not. Like here I would like to mention one thing, that if it is a function that takes two arguments, that you can check the Lipschitz of, means whether the function is Lipschitz or non-Lipschitz with respect to one argument itself. So the function failed to satisfy f of t x1 minus f of t x2, because x1 plus x2 can any value, even if you keep t constant, then also for x1 plus x2 can be very large. So basically your function rate of, means f of t comma x1 minus f of t of comma x2, you are finding the rate of change of the function, and the whole idea behind the Lipschitz is that the rate of change of function is less than the rate of change of your function ordinate. Rate of change of your function is less than the rate of change of its argument. That is the whole idea. So here, if that is the case, then you can see that this function fails to become Lipschitz with respect to this. But for finite x, you can see that this function holds good for Lipschitz with respect to t. Like if I ask you to check its function for t, then what you will get, instead of considering variation for x, you need to consider the variation for t. So you will need to pass t1, t2 through that function, and you will get something x square inside that norm t1 minus t2. So for all finite value of x, you will get that the function L will become x square. So this function is Lipschitz with respect to t, but it is not Lipschitz with respect to x1, x2. Another one, we can prove that if we take a rectangle, any rectangle, how to represent a rectangle? Like you can represent it like where this close end gives you one side, say here A, this is B, and CD is say this side. So when you take the Cartesian product of this set, you will get a collection of all points that is there in the rectangle. Now you can see that the same function which was not Lipschitz, now can we find it? Like if we take that same function here, what we will see that t norm x1 plus x2, that was the issue in the previous case. It was going out of bound when either x1 or x2 or x1 plus x2 was going out of bound. However, if we consider that function variation, like if we consider that function is bound to pick up x within this range, where it can vary only in this region, then what you can write, like this point it can pick up, like you can write this t x1 plus x2, how much it can be? It can be less than is equal to 2 max a comma b into max c comma d, right, on R. So if that is the case, then we can find out that this function becomes elliptic in this rectangular area. So we can say that even if it is not globally elliptic, we can show that for certain region it becomes elliptic. One more example that we use regularly, that is if we consider the time variation of your unit step function, you will see that in this region where there is a sudden jerk from 0 to 1, at that zone the function is not elliptic. But if you take any value of time t greater than 0, then the function is perfectly elliptic in this region. So I hope you get some idea about elliptic function. Now let us first discuss the first theorem, that is theorem of local existence and uniqueness. What does that theorem state? That let f of t comma x be piecewise linear, no, not piecewise linear, sorry, piecewise continuous in T and satisfy the elliptic condition for x like for all x1 comma x2 inside a ball B is equal to x belongs to Rn such that x minus x naught less than is equal to R. Then there exist some delta greater than 0 such that the state equation x dot is equal to f of t comma x with x t naught is equal to x naught as a unique solution over T0 to T0 plus delta. So let us first understand this thing very carefully, that for all let f t comma x be piecewise continuous in t. Now, what is piecewise continuous? What is piecewise continuous function? Let me draw a diagram that will help you. Say you have a function piecewise continuous with respect to t. So let a function f of t comma x, but we are not considering its variation for x. We are considering its variation for only t. Then what you will get? It will behave like function. Now, obviously here, if you consider n-dimensional function, then this f t comma x, there will be n number of components like f1 t comma x, f2 t comma x, and at the end fn t comma x. But we are not considering that. We are considering that we consider any one of them to understand what is piecewise continuous. However, if it is an n-dimensional system, then all the n functions like all f1, f2, fn, all of them are piecewise continuous. How to draw the piecewise continuous variation? Like if f1 t, say so, you can see that these are the different regions where the functions are having continuous value. Now, another function that may have a different value like even there is no necessity that the piece or the size of interval that you have picked up for first function will be the same for the second function. There is no such necessity, but only thing is that the function is such that it can be represented as a piecewise continuous function in every open subinterval. Now, here, just a minute, let me check whether it's recording or not. Hello, hello, okay, it's recording. Now, here you can see that we got some idea about piecewise continuous function. Now, piecewise continuous in t. Obviously, if it is piecewise continuous in t, and if we claim that piecewise continuous in x, then Laplace condition is much more stronger condition in that way. But satisfy the Laplace, not Laplace, Lipschitz condition is much more stronger condition in terms of continuity. This remain valid within the region of a ball that is defined by, this ball is defined in such a way that we have studied norm. So this is the Euclidean norm, right? X belongs to Rn. I'm trying to give you a pictorial view of this. Like you have a three-dimensional system like this. Here you are having x naught. Now what it tells that this ball is such that it is like you are having a ball around this point, So how this ball is defined? If this is our x naught, the center of this ball, then any point on that means outer surface of the ball is at a distance, means any point if you take the Euclidean distance from the center of the ball is always less than r, means always is equal to r, means if r is the center of, means r is the radius of the ball, then we can write, say any point here we are taking x1 dash, x2 dash, x3 dash. So we can write x1 dash minus x naught 1 whole square plus x2 dash minus x naught 2 dash x naught 2 whole square, because here in a three-dimensional space if you want to mention, say this is x1, this one is x3 and this one is x2, this side minus x2, this side you are having minus x1, this side you are having minus x3. So any point you need three coordinate, so accordingly your x0 will also have a tuple like x01, x02, x03, so that will be x03 square. So this x1 dash, x2 dash, x3 dash, they are variable, they are moving on, like you have placed a football with center at x0 and this one defines the outer surface, then this will be equal to r, and if you move inside that football then it will become less than r, right? So in this region only we can get this condition is being satisfied by the function. Then for some delta greater than 0 we have a closed interval over time t0 to t0 plus delta, in which we will get an exact solution. Now obvious question that may hit you, like what is the point here? Like we are defining the local what we are trying to define, that localness in terms of the state variable x, not in terms of time. But while defining the range of solution, we are defining it t0 to t0 plus delta. The idea behind this is very simple. Like you know how your every x1 is related to your x1 dot. What I am trying to say, from where this all this means jargon or this theorem comes, let me explain you. You see here one thing that is very easy to understand, which we call the epsilon delta theorem for continuity. You must have studied it in your 12th standard. So what says in that epsilon delta definition of continuity? I would like to give you an informal description, like close points delta apart in domain maps or are mapped to close points epsilon apart. So formal definition is that a function from R to R is continuous at a point P belongs to R if given epsilon greater than 0 there exists delta greater than 0 such that P minus x less than delta implies Fp minus Fx less than is equal to epsilon, or sorry, less than epsilon. Well, so how this concept of continuity is applicable here? See, here if you consider our state vector components, like, let me write once again, if you consider an n-dimensional system, you are having here f1 t comma x, f of 2 t comma x, then f of n t comma x, right? Now see that we are claiming that x belongs to Rn, fine, we are also okay with that, but we are claiming that all these functions are Lipschitz with respect to x. Like if we pick up two distinct points, say xa, xb within a region defined or for all means belongs to B such that B contains all x such that norm of x minus x naught less than is equal to R, then basically what you are saying that for all f1, f2, fn, you are picking the 2 points, or even your 2 extreme cases when the 2 points are very far away, they are the 2 points based on our statement of the theorem, the way we have presented this theorem, the points of x with respect to which we are considering all this, they are bounded to lie within a ball B of certain radius r. Now as the function is Lipschitz, so obviously with respect to x your variation is bounded by certain constant, that is the Lipschitz constant. For f1 you can have L1, for f2 you can have L2, for fn you can have Ln. But as all these n functions are Lipschitz, you will have all the n constants, all L should be finite. Now back to the business, like here what we can say that if we take two extreme points xa and xb, they are maintaining Lipschitz relation. So obviously you can consider xa is your starting point and xb is your terminating point. So for that, in this region your function f is Lipschitz, and also you have claimed that this function is piecewise continuous with respect to t. So we can say that this xa to xb, we can claim that this is basically the band epsilon, and for that we will get a corresponding time band, like you are considering state traversal from point xa to point xb. So as the state functions, or means all the state variables, they are continuous function or piecewise continuous function of your time t. Obviously, they will lie inside a band of delta. Like here, if your two state points are obliged to means lie inside a means confined zone, then obviously in time you need only a finite amount of time delta to traverse from one to another point. The way you have defined the state function with respect to time, it only needs a finite time to travel that finite distance in that region. So here we are getting this, the second part. Now this is all about what I have discussed. It is intuitively we are discussing. We can have a formal proof of that. If you want, then you can prove it. Now but this proof is not very important to us, because we are not mathematicians. Rather, we just try to figure out, or try to not figure out, rather to gain much more insight from this problem. So if we consider that one equation which we started with, like x dot is equal to x to the power 1 by 3 with initial condition x0 is equal to 0, then what we will see that this one fx, is it Lipschitz? Let us check. Your f of t comma x is x1 to the power 1 by 3. So let us take f of t comma x1 minus f of t comma x2. So what you will get here, it will give you norm of x1 1 by 3 minus x2 1 by 3, right? Now in this juncture it is difficult for you at x is equal to 0. If you take, then what you will get here is that, or in other way you can also show it that it is not Lipschitz. Like you can carry out what is the value of f dash x. F dash x will become 1 by 3 x of minus 2 by 3. Now as we have said, at t is equal to 0, xt is equal to 0, you can see that at x is equal to 0, this f dash x tends to infinity. So this is not Lipschitz at origin. Therefore, you cannot get a unique solution for this one.